This conference will now be recorded.
Everyone, so we'll start with qualitative analysis, which we have already started in last class. Qualitative analysis of organic compounds. Now, some primary idea we have seen, and among this primary idea, I'm trying to say the Lasagne test, which we do for detection, qualitative detection of nitrogen, sulfur, and halogen, mainly these three elements. Now, as you can see, after sodium fusion test or Lasagne test, here sodium is interacting with the elements carbon and nitrogen, and it is forming sodium cyanide. So this will happen when nitrogen is present, and we need not say carbon separately because carbon will always be there, because we are talking about organic chemistry, so carbon will always be there. Then if sulfur is present, we will get in the sodium extract the sodium salt of sulfide ion, Na2S. If both nitrogen and sulfur are present, and insufficient amount of sodium is used. So if these conditions are present, then we will get NaSC and N. All together we will get sodium thiocyanate, NaSCl. And if halogens are present, chloride, bromide, iodide, it is not applicable for fluoride, then we will have the salt formation, which is sodium halide, NaX. Now this X may be Cl, it may be Br, or it may be I. Now we will see one by one what are the actual reactions, that is the detailed reactions for all these three different elements detection. So first we will focus on detection of nitrogen. So when it is detection of nitrogen, we will take around 2 ml of sodium extract, and that sodium extract, that is the fusion test that we have done, details we have seen, details of the procedure we have already learned in the last class. So that extract you have to take around 2 ml, and you have to treat it with 3 to 4 drops of fresh and saturated solution of ferrous sulfate. Now fresh and saturated solution must be, this condition must be fulfilled. If it is already made for long time, that solution we can't use. We have to make it freshly and it should be saturated. Now why it should be fresh? Details of what is the reason behind that, we will study that separately. Right now just focus on the procedure. So 2 ml of sodium extract we have taken, with it we have mixed 3 to 4 drops of fresh and saturated solution of FeSO4, ferrous sulfate, where oxidation state of iron is +2. And after that you have to add 2 to 3 drops of NaOH, sodium hydroxide. Now we will boil it for some time. So the reactions that will take place, first of all, ferrous sulfate in presence of sodium hydroxide, it will produce ferrous hydroxide and sodium sulfate. So it is simply exchange of ions, right? Now this ferrous hydroxide, FeOH2, we already know when nitrogen is present, there will be presence of sodium cyanide in the fusion, that is the extract. So this sodium cyanide, now it will react with FeOH2, ferrous hydroxide, and it will form Na4FeCN6. Now this complex is called sodium ferrocyanide. Sodium is the cationic part, so we are writing the cationic name first, sodium and ferrocyanide. Their oxidation state of iron is +2. So it is easy to understand, and it is not that simply you have to memorize it. Ferro means iron is having 2+ oxidation state. If it is +3, then it is ferric. And why these names are important to know, because sometimes if you are getting question where in the options A, B, C, D, there will be suppose some IUPAC names are given, not the formula. And then if it is asking that what is the compound that is formed during this reaction, then you have to understand that it is talking about Na4FeCN6. So the corresponding IUPAC name, if you have proper knowledge, that is also good. So sodium ferrocyanide, iron is having +2 oxidation state, so that is why the name is ferro, not ferric. So +2 oxidation state with 6 Cn minus, that means extra negative charge, +2 minus 6, extra negative charge -4, which is balanced by 4 Na plus ions. That is why the formula is like this. And this will be the byproduct. Now this sodium ferrocyanide that is formed, it is shown in single step, but it may be more than, you can write it in more than one step. So this step, if I break in 2 steps, now what will happen? So both this, that is, if you write it in single step, that is one type, and if you write it in 2 different steps, that is another way to show these reactions. So FeOH whole 2 in presence of 2 NaCN, first it will produce FeCN whole 2, 2 NaOH. Now this FeCN whole 2, iron is +2 oxidation state. Now it will react with 4 NaCN and it will produce Na4 FeCN6. Now these two equations, if you add, basically you will get the equation that is already mentioned here. So what will happen here? Some compounds will be cancelled. FeCN2, it is present both sides. For the second equation, it is on the left hand side. For the first equation, on the right hand side. So these two will be cancelled. These 2 NaCN, 4 NaCN together, it will be 6 NaCN that you can see here. FeOH whole 2 left hand side and right hand side, you have, this is the main product, and 2 NaOH. So these two equations, if you combine, basically you will get this equation. Now what will happen? After formation of the sodium ferrocyanide, next we have to add 2 to 3 drops of ferric chloride solution. So this is having oxidation state +3. And not just ferric chloride solution you are adding, you also have to acidify it by hydrochloric acid. Next, once you do this, there will be formation of Prussian blue or greenish blue precipitate, or even if it is, there is no precipitate, even if it is simply the coloration is appearing, that may also happen. So all this, whatever it happening within this, that is, it may be formation of some PPT having greenish blue or Prussian blue color, or if there is no PPT, simply coloration. So whatever it is, it always indicates the presence of nitrogen. So what is happening here? Sodium ferrocyanide, which is already formed in the previous step, now it will react with 4FeCl3. 3 moles of this, 4 moles of FeCl3, and it will produce ferric ferrocyanide. Now here these sodium ions as if replaced by iron. And try to understand the oxidation state. The Fe, which is present inside this coordination sphere, it is already having +2 oxidation state, and the Fe that is present outside the coordination sphere, that is actually having +3 oxidation state. So that is why the name is ferric ferrocyanide. Cationic part is ferric, and that part is always written first in the IUPAC name, and then it is ferrocyanide. So ferrocyanide here also written like this, here also it is written like this. Only difference is now the cation exchange, instead of sodium, now it is iron 3. So the name is changed from sodium ferrocyanide to ferric ferrocyanide. So if you learn in this way, that is what is the logic behind this type of formula, then it will not be very difficult to remember. Okay. So Fe4 FeCN6 whole 3. The formula is little different. In the previous case, it is Na4 FeCN6. It is not whole 3. But now you have to place whole 3 for 4 Fe. Why? Because if it is +3 oxidation state and you have total 4, that means total positive charge will be +12. So +12 must be balanced by -12, so that overall it is neutral. Now FeCN6, it is +2 and 6 ion, that means total negative charge 4 minus. So 3 to 4 minus is -12. So that is why the formula is Fe4 FeCN6 whole 3. So always study in this way. What is the logic behind it? What is the explanation behind it? Why the formula is like this? Why it is Na4 FeCN6, but when it is Fe, now it is Fe4 FeCN6 whole 3. So if you know the reason, you don't have to simply memorize it. You can easily understand it. And 12 NaCl, these are the byproducts. Now we will actually try to understand why we have added fresh solution of FeSO4. Now this is important because if you are not using fresh FeSO4 and if you keep it for a long time, suppose you have made it 7 days before, so what will happen? There will be some aerial oxidation and Fe2 plus that will be converted to Fe 3 plus because of aerial oxidation. And now the formula will also be different, Fe2SO4 whole 3, because now the oxidation state is plus. But that is not desired. So this is the reason why we should use fresh solution of FeSO4, not any old already prepared solution. So this is the first reason, the first thing that we have to take care when doing this detection of nitrogen experiment. Now why we are adding HCl? Here it is mentioned in the second step, 2 to 3 drops of FeCl3 added and acidified. That means you are adding HCl. But why? HCl is added to convert this ferrous hydroxide, which is basically dirty green precipitate. It is having dirty green precipitate appearance. Now, if it is already formed, if it is already present in the medium, and you are trying to understand this ferric ferrocyanide, which will have some greenish blue or Prussian blue precipitate or coloration, now there may be some interference, because this is also having some greenish blue, and FeOH2, that is also green precipitate, so there may be some interference. So just to avoid this problem, we add HCl, so that HCl reacts with FeOH2 in presence of HCl. Now it will be converted to FeCl2, which is water soluble, and there will be no PPT formation, there is no such green color, and there will be no interference. So this is the reason these two factors are important, because sometimes you may get question regarding the fact that why HCl is added, why it is acidified, even if it is not HCl, some other acid. Important point is why we are adding acid, because to convert FeOH2, which is having some green PPT, and it may cause some interference. So remove that, we use HCl. This is the reason. After nitrogen, detection of sulfur. Again, we will take 2 ml of freshly prepared sodium nitroprusside solution. Now, what is sodium nitroprusside solution? It is this formula, Na2FeCN5NO. 2 sodium ion outside the coordination sphere, inside Fe with 5 cyano and 1 nitrosin. So this is now added. Now, this solution is colorless. There is no color. Now, this is added to 1 ml of sodium extract that you have made. Now, under this condition, if there is violet or purple color generated, then it proves the presence of sulfur. So, what is the difference happening here? Now, these 2 sodium ion combining with these 2, and now it is having Na4, total 4 sodium plus ion. Okay. Here, oxidation state of iron is +2 and 5 cyano ligand. That means 3 negative charge, but from NO, 1 negative charge is neutralized. So you are now left with plus -2 charge, which is balanced by 2 Na. Now Na4. So Fe, now there will be 5 cyano, so negative charge will be there. From NOS also there will be negative charge. So as a result, there will be total 4 negative charge extra. And as a result, what will happen? This 4 negative charge, that will be balanced by 4 sodium ion. Fine. And this will have some violet color. So if there is this type of observation is there, so we can say that sulfur is present. So this is the first test that you can do for sulfur, but that is not the only test. You can also do some other test for sulfur. So the second test for sulfur, this is number 1, this is number 2. So this is alternate test that also you can do just to confirm whatever you are seeing, that violet color. 2 ml of sodium extract we will take, and that will be acidified by acetic acid. Then 2 ml of lead acetate solution we will add. So 2 ml sodium extract acidified with acetic acid is added. 2 ml of lead acetate. Lead acetate is this one, CH3COO whole 2 Pb. So Pb is having +2 oxidation state, which is balanced by 2 CH3CO minus R. And when we have sulfur in the organic compound, in the sodium fusion extract, you already have sodium sulfite, Na2S, and that sodium sulfite will react with this. There will be simply exchange of cations and anions. Now S is with Pb, and there is some black PPT formation plus sodium acetate, which is the byproduct. Okay. After sulfur and nitrogen detection, we have seen two separate experiments. One is for nitrogen, another one is for sulfur. But suppose sometime it may happen that both nitrogen and sulfur are present in the organic compound. Then there is a chance of formation of sodium thiocyanate, SCN. Now, not just N and S both are present, another condition also there must be present. If N and S both are present in the organic compound, and if the extract is prepared with insufficient amount of sodium, because if sodium amount is not insufficient, that is if it is sufficient, then NaSCN will not be produced. So not just N and S both are present, but insufficient amount of sodium also if present in the medium. Then only NaSCN will be formed instead of sodium cyanide. Okay. Now not NaCN, but NaSCN will be produced. This NaSCN, when heated with ferric chloride, there will be formation of blood red coloration. Remember in the experiment of nitrogen, that is the first slide. Here we have seen in the last step we are adding FeCl3. But if there is already sulfur is present, there is presence of NaSCN, and if you are using insufficient amount of sodium, then in the medium NaSCN is there. You are doing the test of nitrogen, you are adding FeCl3, you may observe blood red coloration. Okay. So NaSCN plus FeCl3, now FeSCN whole 3 is formed and 3NaCN, which is also simply exchange of ions. Now, as a note, we have to remember that suppose you are not getting this blood red coloration, but that doesn't necessarily mean that sulfur is absent. Why? Because insufficient amount of sodium, if it is not present, then you will not get this observation. So mere absence of blood red coloration, it doesn't prove that sulfur is not present. This is due to the reason that presence of excess of sodium metal. Suppose sufficient amount of sodium is there, not insufficient. Then what will happen? This NaSCN ultimately will decompose to form NaCN and Na2S. So now they are behaving as if S and N, they are separate. That is separate sodium salt of sulfite and sodium salt of cyan. Now they are not together when there is excess of sodium. But as we do not take sodium always after some measurement, we simply take it. So there may be sometimes that it is present insufficient. So only in that case you will get blood red coloration. But if it is present insufficient, then 2Na plus NaSCN, as you can see in this equation, Na2S and NaCN will be formed separately. And in this case, sulfur and nitrogen are to be identified in separate test, not any blood red color formation because of this FeSCN whole 3 compound. Fine. Now we will solve this question based on whatever we have studied. Which of the following compound will give blood red color while doing lasagna test? Now blood red color, that is because of formation of FeSCN whole 3. We have just seen that. So there must be presence of NaSCN, which in presence of FeCl3. Now Na is replaced by Fe. But if both sulfur and nitrogen not present, this type of observation is not possible, right? At least both of them must be present. Now look at the options. The first option is NH2CONH2, which is urea. NH2CONH2. Now in this molecule you do not have sulfur, you have only nitrogen. Second compound NH2C6H4SO3H. This is basically aromatic compound. SO3H, and though positions we do not know, but whatever is the position, ortho, meta, para, it doesn't matter. both sulfur and nitrogen present. So this should be the correct answer. And look at the other two options. H2SO4, it is inorganic compound and there is no carbon. So no question of NaCN formation, and sulfur, only sulfur is there, but nitrogen is also not present. Then CHCl3, there is no presence of sulfur or nitrogen, only carbon is present. So only option B will be the correct option. We'll go to the next question. Which of the following compound will give positive Lasagne test for nitrogen? Now, to get positive test for nitrogen, there must be formation of NaCN, right? After sodium fusion. Now, if you look at these compounds, they are actually not organic compound. But that is not the point. You just have to understand whether both carbon and nitrogen are present or not. Now, the first molecule NH2OH, there is only nitrogen. You do not have any carbon. Here also you do not have any carbon, NH2NH2, right? So how this NaCN will be formed? But we have KCN. So KCN will give, basically it is already in the form of some NaCN. Just instead of Na we have K. So if you do fusion test with this compound, it may be converted to NaCN. Even if it is not converted, if you do the test directly with KCN solution, then also you will get the positive test. Remember the experiment for nitrogen that we do. First we add ferrous sulfate solution which is freshly prepared. Then we add FeCl3 and there is some conditions that we have to maintain, that is alkaline condition, acidic condition. So if we do all these things for KCN, we can get the positive result. In the Lasagne test for nitrogen in an organic compound, the Prussian blue color is obtained due to the formation of, we know when there is nitrogen present in this Lasagne test, there is some, in the final step, there is Prussian blue color or any greenish blue, PPT or coloration, anything may happen. But this is because of which compound? It is obviously a complex. And in this complex, we have FeCN6 inside the coordination sphere, but that is present in all the options. And outside the coordination sphere, there is basically iron, not sodium. That is a final compound if you consider there is iron present inside the coordination sphere, also outside the coordination sphere. It is basically ferric ferrocyanide. So ferric ferrocyanide means the outside coordination sphere, it is having +3 oxidation state and this one is having +2 oxidation state. So total positive charge outside the coordination sphere, it is +12, inside it is -12. So together it will be neutral. So this is the compound which is responsible for this type of specific color generation when nitrogen is present. Don't think that option A is the correct option because that is produced before you are adding FeCl3. Okay, this is also produced, but this is not the final compound. Final compound is this one which is having Prussian blue, not the previous compound which is Na4FeCl6, and these two are never generated. Only these two compounds we have seen in this experiment, but actual color, that is Prussian blue color, that is because of the second compound. In Lasagne test for sulfur, the purple color formed after the addition of sodium nitroprusside. So sodium nitroprusside you have added, there is some violet or purple color generation, and that is because of some compound where Fe is attached to not just Cn but it is also attached to this type of NOS. So these two you can easily cancel, right? Now total, that is outside, how many sodium ions are present? So inside we have Fe which is having oxidation state +2. Now +2, then we have -5 from cyano and -1 from this. So together it is 5 and 1, 6. So extra negative charge is -4. So it must be balanced by 4 Na. So in this way you can remember the formula, right? Na4FeCN5NOS. So next we will go to the question. Okay, we have done all the question. Next we will go to detection of halogen. So we have finished detection of nitrogen, detection of sulfur separately, and also we have seen when both of them are present together and insufficient amount of sodium is present, there is a chance of formation of FeSCN3 when you are adding FeCl3, which is having blood red color. Now the third element, though it may be more than one element, but all of them are halogen, same type of element. Now these halogen, when we are saying, it is basically ClBrI, not fluorine. ClBrI. Silver nitrate test. Here we will do basically two tests. Though the first test is mainly done, but there is another experiment also, which sometimes is used for confirmation. That is some added advantage. That is one test you have already done, you already know that halogen is present. That is fine. But if you are doing another test and again you are seeing some positive results, so now there is no doubt that halogens are present. Silver nitrate test. So as the name suggests, so there must be the use of silver nitrate, right? So 2 ml of sodium fusion extract, we will boil with 1 ml dilute HNO3. So not just simply you are adding HNO3, you are also first acidifying it with dilute HNO3, then you are adding HNO3. Now depending on whether Cl is present, Br is present or iodine is present, there will be slight difference in observation. Try to understand this observation, because this difference will only help you to differentiate that which halogen is actually present. Because it is not enough information. You know that some halogens are present, but which halogen is present, that also you have to know. Right? If it is some Cardi white precipitate you are getting after addition of HNO3 and AgNO3, Cardi white precipitate. Try to understand. Because sometimes precipitate may be of different types of nature. It may be gelatinous, it may be some powder form, it may be cardi. So that is why it is mentioned, especially cardi white precipitate, card-like nature. Now, this will be soluble in ammonium hydroxide solution. That is ammonia in water, ammonium hydroxide solution. So if you are getting this type of observation, then it proves that chlorine is present. So what reaction is happening here? NaCl is present in the fusion extract. In general, I can write in the fusion extract, you will have NaX. When you have done the fusion and in the organic compound with which you are dealing, if this organic compound is having some halogen, now in the fusion extract, you will get NaX. Now this NaX may be NaCl, NaBr or NaI. So here we are talking about chlorine. So that is why it is NaCl. Now this NaCl will react with AgNO3 and there will be formation of silver chloride precipitate. This is insoluble in water, so that is why you will get precipitate. And the byproduct is soluble. So the precipitate is because of silver chloride. And this silver chloride, in presence of NH4OH, there is some complex formation which is basically again soluble. So that is why it is mentioned here. This cardi white precipitate is soluble in NH4OH. Next, if bromine is present, again you will get some precipitate, but now it is not cardi white. There is slight difference. Now it is pale yellow precipitate. So you have to be very careful when you are doing the test. That is the difference in color you have to understand. Even if you are having any confusion, but see, when you will add in the second step, when you will add NH4OH solution, and if you are now seeing that it is not fully soluble, it is partially soluble, then it will prove the presence of bromine. So AgBr, unlike AgCl, which is fully soluble in NH4OH, AgBr is not fully soluble in NH4OH. So that is the reason now it will be partially soluble. So these are the slight differences which will help us to understand which halogen is actually present. Because when there is halogen, you will always get some precipitate. But which this precipitate is indicating ClBr or I, that is the next thing to understand. If iodine is present, again you will get some precipitate, but now it is yellow color precipitate. And it is not soluble at all in NH4OH, unlike AgCl, which is fully soluble, unlike AgBr, which is partially soluble, but now it is silver iodide, which is not at all soluble. And it indicates the presence of iodine. And in each time there is same type of byproduct because it is simply exchange of ions, displacement reaction. Okay. Second reaction that you can do for detection. Obviously, this is the main experiment that you have to do for detection of halogen. But if you are interested to, if you are having some doubt, again you can do another test which we call chloroform test. So in this case what we do, we take again sodium extract and we acidify it with dilute HNO3, just like in the previous case also we have done it. But now instead of HNO3 we are adding 2 to 3 drops of chloroform, which is CHCl3, or you can add carbon tetrachloride. After addition of this, now these two are basically not used as reacting agent, it is basically used as solvent, followed by chlorine water. Now you may be thinking that we are doing halogen test, then why we are adding chlorine water? Remember, this chloroform test is only for Br and iodine. It is not for chlorine, right? So if you are already know that Br or I is present, you want to confirm it again, then you can do this test. So in this case, this chlorine water basically we are using as oxidizing agent. Okay. So what it will do, suppose in the medium you already have NaBr, this chlorine will oxidize Br minus to Br0 and itself will be converted to -1. So chlorine having this type of oxidation property, and that is the reason now as free bromine is present and in the medium you already have, it is not just aqueous medium, you have already added some organic solvent, chloroform or CCl4, any one of these. So that is, it is called chloroform test if you are using chloroform as solvent. Now this CH3 layer, that is the organic solvent layer, or it may be CCl4 layer, it will convert to pale brown color. Now why it is happening? Because bromine, when you have bromine in CHCl3 medium, it is having this specific color. So it will help us to understand that bromine is present. Remember, in the differential, that is in separating funnel, we have learned some purification method. There we have seen that two layers are generated, immiscible, because water is immiscible with organic solvent. So it is also just like that. There will be two layers, one layer is aqueous, another layer is organic. And in the organic layer, bromine will be showing color which is brown, pale brown. So this is for bromine. So this is chloroform part and this is water part. Okay. So in the chloroform part, you will have this type of color. Now if it is sodium iodide, again chlorine will oxidize iodide ion -1 charge to 0. Itself will accept electron and from 0 oxidation state, now it will be converted to -1. Now CHCl3 layer, it will be converted to purple or violet color that you can see here. And remember, it is not for chlorine because we are using chlorine as oxidizing agent. Now some important note during the experiment of halogens, detection of halogens. It is not possible to detect the presence of fluorine because whatever we have learned in the previous section, there you have not seen any test for fluorine. So it is not for fluorine. Why? Because in each case, whether it is AgCl, AgB or AgI, you have seen some precipitate formation. But this precipitate is possible only when X is Cl, Br or I. But it is not for fluorine because AgF is in not having any insolubility in water. It is soluble. So how you will get precipitate? So you will not get any observation. So as there is no precipitate for AgF, so this test is not for fluorine. Okay. And the second important notice, suppose you already know that nitrogen or sulfur are present in the organic compound and formation of black precipitate of AgCN and AgS may interfere during the test because in the test for halogen you add AgNO3 after acidification, but this AgNO3 where Ag plus cation is present, this Ag plus can react with Cn minus or it can react with sulfide. Sulfide 2 minus is present. So this is only for when nitrogen is present and this is for when sulfur is present. Now, if this type of black PPT is formed, and suppose there is also PPT of AgCl or AgBr, but there will be confusion because the PPT from AgCl, AgBr, AgI, they are basically carding white or pale yellow or yellow. But if you are having some black PPT, obviously there will be some interference. You will not be able to understand whether some white precipitate is also there, because when there is black PPT, it is not possible for us to recognize the white one or the pale yellow one. So what we have to do, there must be some extra step that using which we have to remove this cyano and sulfide so that there is no interference. So how to do that? To remove this lasagna extract is first boiled with concentrated HNO3 or glacial acetic acid. So in the previous case, we have seen we are simply hitting it dilute HNO3. But if you are suspecting that nitrogen or halogen, sulfur is also present, you have to boil it very well with glacial acetic acid, that is concentrated acetic acid or concentrated nitric acid, to decompose NaCN or Na2S to the form of HCN or H2S. So from NaCN, now we are converting it to HCN form. Na is simply replaced by H. Now HCN and Na2S, which is converted to H2S. Now these two you can easily remove, because now these two compounds are in the form of gaseous, and removal of gaseous are easy. So cyano and sulfide ions are removed from the extract in the form of HCN gas and H2S gas. NaCN reacting with HNO3, it is converted to sodium nitrate and HCN gas. From the sign you can understand this is gas. This is also gas. So once it is removed, now in the medium you do not have any NaCN or Na2S. You can simply do the normal test for halogens and there will be no interference. So these things we have to keep in mind. After detection of halogen, next the last element, detection of phosphorus. See, if we though it is a rare case because hardly you will get any phosphorus in the organic compound, but we will also study this one. Phosphorus is detected by fusing organic compounds with an oxidizing agent, that is sodium peroxide. Now this test is not under lasagna test. Lasagna test is only for nitrogen, sulfur and halogen. This is separate, okay? This is not with sodium fusion extract. You are simply doing it. That is only for phosphorus if you are suspecting it is present. So first we will fuse the organic compound with some oxidizing agent, which is sodium peroxide. When phosphorus will be oxidized to phosphorus will be, which is present in the organic compound, that will be oxidized to Na3PO4, sodium phosphate, and Na2O. Now this sodium phosphate, the fused mass is extracted with water, that is this one extracted with water. Aqueous solution is boiled with concentrated HNO3. So this Na3PO4, now it will react with nitric acid, and these sodium ions, now it is replaced by H. So now you have H3PO4. This is a byproduct. Fine. Now once this is formed, the next step is solution of ammonium molybdate is added to the above solution. If phosphorus is present, you will get canary yellow coloration or PPT. Coloration means simply color generation. PPT means PP precipitate will be there. And this PPT is because of the formation of ammonium phosphomolybdate, which is actually representing the presence of phosphorus. So this type of canary yellow PPT you will get, and the reaction that is involved here, H3PO4, which you have already generated in this step. This is step 1, this is step 2. In step 2 you have generated H3PO4, but this will be possible only if phosphorus is present. Now this H3PO4 in the third step, it is reacting with ammonium molybdate. This one is ammonium molybdate, NH4 MoO4. So 12 moles of ammonium molybdate molybdate ion is MoO4. This part is molybdate ion. So 12 moles of ammonium molybdate, and there is already presence of HNO3. So together, this is the balanced equation, as you can see, and it will now produce ammonium phosphomolybdate. So this is actually the reason for this canary yellow precipitate. Okay. So NH4 whole 3 PO4, then 12 MoO3. So it will be 12 H2O and ammonium nitrate, that will be the byproduct. But remember the name of the compound for which you are getting this type of canary yellow precipitate formation. That molecule is NH4 whole 3 PO4 ammonium phosphomolybdate. So in this way we can understand whether it is present or not. Fine. So it will be 2 NH4 whole 2 MoO4. There will be 2 negative charge from this part. It is something like this. So 2 negative charge, that is now balanced with 2 NH4 plus. Okay. Here we have a question. Sodium extract is heated with concentrated HNO3 before testing for halogens. So this question is related to halogen detection, and in halogen detection we first heat it with HNO3. Especially concentrated HNO3 is required if you are suspecting there is presence of sulfur or nitrogen. So this reason we have already learned 2 slides before. So it is simply in this question it is asking that why sodium extract is heated with concentrated HNO3 before the silver nitrate test or halogen. Now look at the options. First option is saying that sulfide ion and cyano ion is present. They are decomposed by concentrated HNO3 and there will be no interference. Then silver reacts faster with halides in acidic medium. Ag2S, AgCN are soluble in acidic medium. Silver halides are totally insoluble in nitric acid. Now these two are obviously not the reason that silver reacts faster with halide. There is no such thing. Then silver halides, that is AgX, AgCl, AgBl like this, totally insoluble only in nitric acid. No, that is also not the reason. Then Ag2S, AgCN, these two compound can be formed only if you have presence of sulfide ion and CN-. And they are not soluble. They will actually make some black PPT. So this is also not the correct statement. First one is the correct statement because if these two ions are present, there will be interference by the formation of Ag2S, AgC and black PPT. That is why first we use concentrated HNO3. Corresponding reaction we have already seen. And these two are converted to H2S and HCl. These two are gas, can be easily removed. Now there is no interference. This is the actual reason why we boil it with concentrated HNO3. Now this question is from the name of this molecule, you can understand this is for phosphorus. An organic compound A oxidized with Na2O2 followed by boiling with HNO3. The resultant solution is then treated with ammonium molybdate to yield a yellow PPT, canary yellow PPT. Based on the above observation, the element present in the given compound. So this explanation, this information is basically explaining the experiment that we have just learned. See, first step you are using some oxidizing agent, sodium peroxide. Second step you are boiling with HNO3. Third step you are adding ammonium molybdate. You are getting some precipitate. Now this is for phosphorus. So that is why here correct option would be this one, phosphorus. Okay. So now we have finished the qualitative analysis of organic compounds, and once we have done it, now it will be quantitative. So when it is quantitative, we will actually find out the amount present. Suppose we are talking about nitrogen. So how much nitrogen is present in the compound, in the organic compound? That is in the percentage form that you can find out. And there is different methods for this. quantitative analysis of organic compounds. So the first method we are going to discuss is the estimation of carbon and hydrogen together, and that is done by Liebig's combustion methods, carbon, hydrogen. Remember the qualitative test for carbon and hydrogen, where we have used some hard glass test tube, inside of which you have taken the organic compound plus copper oxide, CO, you have heated it strongly. There is generation of water, there is generation of CO2. CO2 is coming from carbon and water is coming from H. Now the same type of experiment you will do actually here again, but now you have to measure the amount of CO2 and H2O that is produced, because now it is not qualitative, it is quantitative. You actually now you are finding the actual amount of the element present in the organic compound. So this is the experimental setup. Same thing we'll do again. Here we have taken this combustion tube. Why we are saying combustion? Because in this case carbon we will convert to CO2 and H we will convert to H2O in presence of oxygen. So here you will take a sample, and this is made of platinum, and the sample must be you should know what is the mass of this sample, because we have to do some calculation. So you have taken some known mass of organic compound. Known mass of organic compound you have taken. Now with it you have added CuO and you are burning it in oxygen. Burn in oxygen, or it may be dry air. So when you are doing this, you are burning this in presence of air or dry air or oxygen. Now why this dry air is important? Because suppose if it is not dry, there is already some moisture present, there will be interference, because we are already producing moisture from H, but if it is already present in the air, that will not help us, that there will be error in calculation. So it must be dry air. So once the reaction is done in the combustion tube, carbon will be converted to, after oxidation, it will be converted to CO2, and H after oxidation it will be converted to H2, right? Now next, so up to this point you have understood here coarse CO is present. So CO is present different form, but ultimately H2 and CO2 will be produced. Now this H2 and CO2, here you can see two U-shaped tube. So in the first U-shaped tube, you have taken anhydrous magnesium perchlorate, MgClO4 whole 2, or you can take calcium chloride, whatever it is, both are fine. Any one of these you will take, and in the second U tube, there will be KOH solution on asbestos. So here you have taken KOH, in the previous U tube you have taken MgClO4CaCl2. Now, what is the purpose of using these two compounds into separate test tube? The reason is that in that U tube where KOH is present, here CO2 will be absorbed, and where CaCl2 or magnesium perchlorate is present, here H2 will be absorbed. Now the tube, that is these two tubes, before experiment, suppose you already know its mass, and after the experiment, that is after the combustion, you will take again the weight. Now difference in weight, that will give you mass of, difference in mass of this tube will give you mass of CO2 and mass of H2O, right? Now once you know the mass of CO2 and H2O, next you have to do some calculations, right? Now as we have said that we have already taken some known amount of organic compound. So suppose the known mass of organic compound that you have taken, it is m gram, and the mass of CO2, that is m1 gram, and the mass of H2O, that is m2 gram. So all these informations We already know it. Now, if you know this is the mass of organic compound, this is the mass of CO2, this is the mass of water. Okay. So next what we'll do in the calculation, mass of organic compound M, mass of CO2 M1, mass of H2O M2. Now, if you do the calculation for H2O first, for water molar mass, as we know, it is 18. For CO2 molecular weight, it is 44, right? That means in 1 mole of H2O, that is in 18 gram of H2O, you have 2 gram of hydrogen. Similarly, in 44 gram of CO2, that is 1 mole, you have 12 gram of carbon, right? Now, if it is so, then M1 gram CO2, that will have 12 divided by 44 multiplied by M1 gram of carbon. And similarly, M2 gram H2O will contain 2 divided by 18 multiplied by M2 gram of H. So, percentage of hydrogen, that will be 2 divided by 18 M2 divided by the mass of original organic compound multiplied by 100. Same is also here, percentage of carbon. So from this you can simplify it. It is actually 2 by 18. You can write 1 by 9. M2 M 100. So these two are the final formula we have reached. If you put the value of M1 M, you can simplify 2 by 18, 12 by 44, and you can get the percentage of hydrogen present. So see, now it is completely quantitative. So in this way, in the next class, we will also see how to quantitatively analyze nitrogen and then halogen. Everything we will see in the next class. We are ending the session here. Thank you for listening.